Okay, given silver chloride, KSP 1.8 times 10 to the minus 10, let's calculate the solubility of that salt in water only. The ionization of silver chloride is 1 to 1. And therefore the solubility is given by x equal the square root of KSP, or square root of 1.8 times 10 to the minus 10 molar. This is of course 1.4 times 10 to the minus 5 in fresh water. Now let's calculate the solubility of the same silver chloride in the presence of a 0.01 molar hydrochloric acid solution. KSP 1.8 times 10 to the minus 10. Now, in calculating solubility in the presence of a common ion, you cannot use the freshwater solubility formulas that we have been deriving. You have to work from the ICE table, and so we'll just start there with the silver chloride ionization to deliver silver ions into solution, along with chloride ions into solution. Now initially we're going to have an HCl solution that's 0.01 in HCl, and this is a strong acid. So therefore it ionizes 100% and then delivers 0.01 chloride. So we're really adding silver chloride into a 0.01 molar chloride solution. And before ionization occurs in the presence of the ion, we write that as the initial concentration. That changes in concentration. We deliver X silver and X chloride, and at equilibrium we have X silver and 0.01 plus X in chloride. Well, in this common ion problem, you can drop X because the amount delivered in solution is so small it won't change this, and we can assume all of the common ion is from the hydrochloric acid solution. So this then is 0.01 molar at equilibrium. And so by solving for X, we also get the solubility of the silver chloride solid. Now we'll set up the KSP expression is 1 to 1, so it'll be silver times chloride, and KSP is 1.8 times 10 to the minus 10. Silver ions X, and the chloride is 0.01 molar. So now we solve for X with 1.8 times 10 to the minus 10 divided by 0.01 moles per liter. So this gives us solubility in the presence of the common ion of 1.8 times 10 to the minus 8. Remembering solubility in water only is 1.34 times 10 to the minus 5 we calculated earlier. We show a significant decrease in solubility in the presence of the common ion. Now, here's another problem. Calculate the solubility of magnesium fluoride in the presence of 0.02 molar sodium fluoride. The solubility of magnesium fluoride in water only is 0.016 grams per liter. And I calculated the formula weight of magnesium fluoride as 61 grams per mole. Well, the first thing we need to do is calculate the molar solubility of magnesium fluoride and then the KSP. So is equal to 0.016 divided by 61 mole per liter. That is 2.62 times 10 to the minus 4 molar in magnesium fluoride. This is water only. Now, from this we can calculate the KSP of magnesium fluoride. I'll make a next note up here. Calculate KSP of magnesium fluoride. So magnesium fluoride ionizes in a 1:2 ratio, which gives us the KSP to equal magnesium and fluoride squared. So we'll need the fluoride concentration and the magnesium concentration. Well, whatever the solubility is for magnesium fluoride in water only is also the amount of magnesium only. So we can write in 2.62 10 to the minus 4 for magnesium. However, the fluoride concentration is 2 times because the 1 mole of magnesium fluoride delivers twice as much fluoride. So we need to double the 2.16 10 to the minus 4. 2.62 10 to the minus 4. That gives us 5.24 times 10 to the minus 4 molar in the fluoride. So now we can apply the KSP expression for magnesium fluoride. So KSP now is the concentration of magnesium, which is 2.62 times 10 to the minus 4 times concentration of fluoride, 5.24 10 to the minus 4 squared. And we see that this gives us 7.2 times 10 to the minus 11 for the KSP of magnesium fluoride. So now we want to calculate the solubility of magnesium fluoride in the presence of 0.02 molar sodium fluoride. Now, we need to keep in mind that sodium fluoride ionizes 100% to sodium ions and fluoride ions. Sodium fluoride is a 1-to-1. So if we have 0.02 molar and sodium fluoride will have 0.02 molar in sodium and 0.02 molar in the fluoride ion when we put in the magnesium fluoride. So magnesium fluoride, solid, ionizes to magnesium ions, and fluoride ions like this. And initially, we have an unknown amount of magnesium delivered into solution by the magnesium solid in the presence of the fluoride. And we assume all of the fluoride comes from the sodium fluoride, and it's 0.02 molar, so 0.02 molar. And so at equilibrium, we'll have X amount of magnesium and 0.02 molar plus X, 2X, but the 2X will drop out as it won't be big enough to influence the 0.2 molar fluoride. Again, we assume all the fluoride comes from the sodium fluoride. So our job now is to determine what X is from the KSP expression, and that would be the solubility of the magnesium fluoride in the presence of 0.02 molar sodium fluoride. So the KSP is equal to magnesium times fluoride squared, like this. Well, the KSP, as we determined earlier, is 7.2 × 10 to the minus 11, which equals X times the concentration of fluoride molar, and we solve for X, which is 7.2 times 10 minus 11 divided by 0.2. That will be in moles per liter. Well, sorry, need to include that as squared. Now we're correct. So this will give us a 1.8 times 10 to the minus 7 molar solution of magnesium fluoride in presence of 0.02 molar sodium fluoride, or the common ion, right there. Remember, in water only, solubility is so we're comparing 1.8 times 10 to the minus 7 common ion to 2.62 times 10 to the minus 4 in pure water. So there's a significant drop, 10 to the minus 4 to 10 to the minus 7 in the common ion. Now we want to look at complex ion equilibrium and formation of a chemical complex with a metal ion functions to increase solubility of salt. Now, the way this works is that an ion, something like, say, silver +1 aqueous, is exposed or placed in presence of something like ammonia gas bubble through a silver solution, and the affinity for silver to bind with the ammonia is extremely high, and we have silver amine complex formed, and this has a formation constant of 1.7 times 10 to the +7. So something with a K value in the 10 to the +7 range would indicate that all of the silver exposed to ammonia would complex with the ammonia and be removed from the equilibrium. So what is happening in the silver chloride before adding the ammonia is in equilibrium with silver ions and chloride ions, aqueous. However, if you put in the ammonia, bubbled ammonia gas through a solution, then this would AgNH3 complex, silver amine complex, would form. And as this forms, this functions to remove Ag plus from the equilibrium. And so we would find that this would have an effect of silver chloride, and there'd be a void right there created because this is taking the silver out of the equilibrium, and as a result the equilibrium would tilt in this direction and shift to replace the removed silver, and ultimately reestablish a new equilibrium with a higher concentration or more the silver chloride dissolved as such. So this was really removed from the system when you had the silver plus and NH3 reacting to form the complex, causing the void in the silver position, which made it lighter on the right side of our seesaw or equilibrium. It would tilt to the left, and so by natural process the silver chloride would begin to break down and shift this to the right to reestablish the new equilibrium. Which involves dissolving more of the silver chloride, and of course the solubility goes way up. Now, the analysis of complex ion equilibria, again, we need to remember that the solubility of silver chloride in water only is 3.14, it's 1.8. I'm sorry. Solubility in water only is 1.34 times 10 to the -5. the expectation in the problem is that the solubility going up because of the complex will show us a result in a number larger than the solubility in silver chloride in water. Well, to deal with this, you have to have two equations, one showing the ionization of silver chloride, or the salt, and then how the salt ion complexes with the other substance in there, and in this case ammonia, if we're forming this silver ammonia complex. So here is how that is presented. And we need the KSP of this one also, and it's 1.8 times 10 to the minus 10. Now the silver will react very quickly with ammonia if it's passed through the solution that contains silver and chloride ions, and that silver ions will react very quickly with ammonia gas passing through, aqueous if you want, and it'll form the silver amine complex in solution, and we'll have also chloride, aqueous. Now this reaction has a K formation constant of 1.7 times 10 to the positive 7. Now these two reactions are added together to get a net reaction, which we apply to the equilibrium expression, and the equilibrium constant for the net reaction is the product of these two, KSP and KF. So we see if we add the silver chloride ionization and the reaction of silver with ammonia, add the two reactions together, silver will cancel out, and then the remaining components would be silver, ammonia, and the silver amine complex, and the chloride ion. This is of course your net reaction, and to get the K complex, that is of the net reaction, it will be the KSP times the KF, which will be 1.8 times 10 to the minus 10 times 1.7 times 10 to the positive 7. So this shows the complex K, our equilibrium constant, to be 3.06 times 10 to the minus 3. It's quite large in most of these. And so as we analyze the equilibrium expression of the complex reaction, we have a change. We can't drop the X in the ice table, and so we have to take that into account because it will influence the overall concentrations. So I'm going to move this up. Let's rewrite our complex equation and apply it to the ice table. And we disregard the silver chloride concentration, but we cannot disregard the ammonia. So let's say we put 0.10 molar of ammonia into the solution, and when the reaction is completed, we get X and X. Well, let's start out with zeros and build our table. Sorry, 0 and 0. Then as it proceeds, this goes down by 2x, and the silver and the chloride, silver complex and the chloride, increase by x and by x. And so we have at equilibrium 0.10 minus 2x, x for the complex and x for the chloride. And the K complex, which we calculated earlier, is 3.06 times 10 to the minus 3. And I'll go ahead and write the expression. So it's products, silver amine complex times the chloride, well, they're all in water, so, and divided by the NH3 gas or concentration squared. So we can take the 3.06 times 10 to the minus 3, set that equal to x times x, or x squared, divided by 0.10 minus 2x, and we square that. Now this expression can be simplified if we take the square root of both sides. So we will take the square root of both sides of this, and so, and that simplifies to 0.055 to equal x over 0.1 minus 2x. And so this is an equation in one unknown, so we'll solve this for x, and so x now is equal to 0.055 times 0.10 minus 2x, which is so distributing the 0.55 through the parentheses, we have 0.0055 minus 2 times 0.0055, or 0.11x, and we can add 0.11x to both sides of this expression and come up with a 1.11x to equal 0.0055, and solve for x, and divide 0.0055 divided by 1.11 molar. That will give us the solubility as 0.05 molar, which is the solubility in the presence of the complex. So this kind of simplifies to the solubility of silver chloride, says with the complex right there, 0.005. So to review and compare solubilities under the different circumstances, here we have in water only, we found the solubility to be 1.34 times 10 to the minus 5. In the presence of a common ion, the solubility 1.8 times 10 to the minus 8, and that was a 0.01 hydrochloric. If you made it stronger, and this would go down even further. And in the presence of a complex, solubility increased significantly to 5 times 10 to the minus 2 molar in the presence of the silver amine complex.